So today is the big reveal for our Mathematician Spotlight. So I asked you guys if you noticed any patterns. You noticed some of them. Somebody mentioned the other day that they are all alive. I think the tip-off to that was that we saw a 97-year-old mathematician who's still alive. Yes, they're all alive. They strictly alternated male and female, except when somebody was giving a talk and then I had to flip them. But they strictly alternated male and female, so they're half female and half male. I don't know any gender non-binary mathematicians. If I had, I would have put one in. And somebody said, oh, the theme is that they're mostly female. And I thought that was sort of funny, because they're actually exactly 50-50. Half of them are white, half of them are non-white. In particular, every week we had 1 or 2 white people and 2 or 1 non-white people. So that's the case. And so I kind of did that because I would love for the mathematical community to look the way that I made the Mathematician Spotlight look. I'd love for it to be half male and female. It doesn't have to be half white, but it would be nice if it were at least half non-white. So that was the idea. You know, you want to be the change that you wish to see in the world, and so I made our environment of mathematicians look the way that I want mathematicians to look. And some, not surprisingly, are LGBTQ. So happy National Day of Silence, which was yesterday, is a day that commemorates the fact that not all LGBTQ people can openly say that they're LGBTQ. So I just wanted you to know, in case you don't know, I'm gay. To me, that means that I'm attracted to women. Women are great. It's a wonderful life. There are many mathematicians and adults in your life and faculty on campus who are LGBTQ, and sometimes it's not so easy to see them because there's no obvious markers. So now that you know me and you have already made your judgment of me, now you know. So of our Spotlight mathematicians, at least 6 of them are LGBTQ. These ones, right? These ones that I have shown you: Moon, Emily, Autumn, Dylan, Harry, and several others. So there we go. All right. Oh yeah, and in addition to my rainbow headband and my clothes, which I tried to make hit most of the colors of the rainbow, I'm also wearing rainbow socks. So there's this thing recently that people wear their pants a little too short, and that's cool, right? It's happened recently, the past couple of months. It's a thing, right? Yeah. So I'm going to roll up my pants today. Somehow I feel like it looks cooler on other people. But I'm just going to try it. You can tell me if you think it looks cool. OK, so great. So otherwise today, we'll continue talking about Stokes Theorem. So we talked about Stokes Theorem for the first time, last time. And today we'll do a bunch of examples, and then also talk about this sort of surface independence property of Stokes Theorem. So Stokes Theorem, just so you remember what happens with it, says that if you have some surface and you're trying to integrate the curl of f over that whole surface, that's the same as integrating just the vector field f itself over the boundary of S as a vector line integral, as long as the two things are oriented compatibly. So we'll do a bunch of compatible orientation today, but it means that if you are walking along the surface in such a way that your head points in the direction of the oriented normal vector to S, that your left arm is over the surface. So you're walking along the boundary with your head in the direction of the boundary normal vector. You want your left arm to be over the surface. So I like to draw this like this and decide where I want the front of my face and where I want the back of my head. So I guess in order for me to have my left arm over the surface, the top one would have to have my face in the front. So here's the face, and here's the back of the head. And so we have to be going this way. And there's the last thing we'll talk about today is that there's sort of a surface independence property of curl vector fields. So meaning when you integrate a curl, you can change the surface to other surfaces. Analogous to when we had conservative vector fields and we were integrating a line integral over them. So when you were talking about gradient vector fields or conservative vector fields, they were path independent. So if you walk from here to Sharples via this path, or if you walk by this crazy puddle avoiding path, you get the same line integral. So that was our path independence property, and we'll have a similar surface independence property for curl vector fields. Okay. Oh, that was the wrong thing to hit, huh? It is now darker than it was before. Let's try something else. Okay, so let's start with an example of Stokes' theorem. So, for example, suppose you have a sideways bowl that's a part of a parabola. So here's the parabola. It's going sideways. And here's the y-axis, the x-axis, and the z-axis. And this is your surface S. And here's the back. There, okay. And there's your surface S, and it's oriented outward. The reason it's oriented outward is because it's very hard to draw vector fields. I mean, surfaces oriented inward. There you go. There it is. S. And we have a vector field which we want to integrate over this surface. The vector field is y minus 1 sine of e to the x, z to the y, x, y, z, e to the x, y, z, and xz plus y. And this is S, this piece of the paraboloid. S is the piece of the paraboloid y equals x squared plus z squared for y less than or equal to 1. So it's like a paraboloid where the up direction is y. So this would keep going up and out, but we cut it off at y equals 1, right there, 1. There you have it. And we oriented it going out. Yeah, compute, please. We are asked to compute the double integral over S of the curl of f dot ds. So the surface integral of the curl. Okay, so the first option is always just to do it. Fine. Here's f. Compute the curl of f. So compute curl of f and integrate over S. But gosh, this seems like quite a tough thing to do. To compute the curl of f is going to be a mess. It's going to have a lot of variables in it. And then to integrate it over S, well, S is a paraboloid. It seems like it might be a mess. So we could do it, but maybe the first thing we should try is using Stokes' theorem and integrating instead over the boundary curve. So let's try that. So option 2, apply Stokes' theorem and integrate over the boundary curve, boundary of S. So this boundary of S. Okay, good plan. In order to integrate over the boundary curve, we have to pick an orientation so that they're oriented compatibly. So it either goes sort of down in the front and up in the back, or it goes down in the back and up in the front. I'm going to draw a person here with their left arm over the surface. Got to have 2 arms. Good. And so the question should be like, is this person walking toward us, and then out, and then upside down? Or is this person walking toward us and up and out and then walking away? What do you think? Are they walking up or are they walking down? Yeah. Yeah. Oh, yeah, right. One or the other. Yeah, see? Up, up. Okay, walking up because if this is their face and this is the back of their head, then when they get to the top, which is the way that I like to be, right side up, the left arm is over the surface. Yeah, it seems to work. Okay, so you want to have the face coming toward you at the bottom and going up on the front and then down on the back. So I didn't say should this be clockwise or counterclockwise, because it depends on which side you're looking from. So the way that it's on the board, it looks like I'm looking at it from this direction, and so it's clockwise. But if I move to this other side and I looked at it from the xz plane, it would be going counterclockwise. So that's why we have this whole thing about standing with your head in the direction of the normal vector and having your arm over the surface when you walk around the curve, because counterclockwise and clockwise aren't well defined in 3 dimensions. Okay, so that's good. So integrate over ds, compatibly oriented as shown. Okay, cool. So, good. So our goal, our idea is that instead of doing the double integral over S of the curl of f dot ds, we're going to use the integral over the boundary of f dot ds little s. Okay? And so what we need to do is we need to parameterize the boundary. So need to parameterize the boundary so that we can integrate over it. Okay, so let's do that. So it's a circle going in the direction that's drawn here. So one thing to do would be to say, well, the circle is, we cut it off with the plane y equals 1, which is parallel to the xz plane. So let's look at this in the xz plane. So I'm going to take this xz plane and go and turn it so that we have the xz plane like this. Here's the x, here's the z, and I'm looking at it from this side. And so the arrows should go up on the right because that's this part, and they should come down on the left because that's this part. Can you see how we took this picture and turned it that way? Okay, that's the idea. So we want to parameterize this thing. So this is just a counterclockwise unit circle. I guess I should say that. If y equals 1, 1 equals x squared plus z squared. So x squared plus z squared equals 1. That's a unit circle. So this has radius 1. Okay, so it's just x equals cosine of t and z equals sine of t. That's all it is. It's just like x equals cos t, y equals sine t, except now the up direction is z. And it's sitting in the plane y equals 1, so the y is 1. So the parameterization, I'll just put this in our standard form. X of t is cos t, 1 sine t. And then in order to integrate this, we're going to need the velocity. So I'll just compute right now. X prime of t is negative sine t, 0 cosine of t. Okay. Yeah, okay. Okay, so now let's integrate this thing. See what we can do. So the double integral, the thing that we want, over S of the curl of f dot d big S is the integral over the boundary of f dot d little s, which we've shown is the integral of f of our parameterization x of t dot x prime of t dt over whichever values of t we needed to sweep out our curve. And this is something I forgot to do. When we parameterized our curve, we also have to say which t's we're interested in. So t, to get this whole circle, it looks like I need t from 0 to 2 pi. So t goes from 0 to 2 pi. Okay, let's do this. So we're going from t equals 0 to 2 pi f of x of t. Okay, we'll have to plug that in. Let's just put in, since we already know what x prime of t is, let's put that in. So that's negative sine t, 0 cos t. And we'll take that dt. So this part right here is just x prime of t. And then let's do f of x of t. Okay, so that means plug in your parameterization, which gives you the x value, the y value, and the z value, into your vector field. So let's do it. So this first term, y minus 1 times sine of something. Well, y is always 1. So y minus 1 is 0. So this whole term goes away. So it's just 0. Okay? Now, I need to plug in cos t1 and sine t in for x, y, and z into this middle term. That's not too hard. I could write it down. But notice that we're going to take the dot product of it with 0. So we actually don't care what it is. it's just some sort of mess that we don't care about. Okay? And then finally, xz plus y. Okay, now we actually have to do this. So x times z is cos t times sine t. So I'll try to write that here. Cos t times sine t plus y is just 1. So plus 1. Okay. Okay. Okay, so that's the idea. This is our vector field at each point t or each time t. And this is our velocity vector. And we want to take the dot product to see how much they're going in the same direction. So let's do it. So this is the integral from t equals 0 to 2 pi of 0 times something is 0 plus something times 0 is 0 plus cos t sine t plus 1 times cos t is cos squared t times sine t plus cos t dt. Okay, and now you just have to integrate this, which is something you can do. So we could even do it. So we could break it into two parts from t equals 0 to 2 pi of cos squared t sine t dt plus the integral from 0 to 2 pi of cos t dt. So the integral from 0 to 2 pi of cos t dt, that's the area under the cosine curve from 0 to 2 pi, which is a full period of cosine. So the area above the curve and the area below the curve cancel out. So this should come out to 0. So this part is 0. You could also do that by anti-differentiating to sine and seeing that sine of 0 and sine of 2 pi are the same. But geometrically, it's because you're finding the area under this thing. And it's 0. Okay, and then for cos squared t sine t, we have to find an antiderivative. It's like a u substitution. I think the antiderivative is like negative a third cos cubed t. Because if you take the derivative, the 3 comes down and cancels out. We get cos squared of t, which is what we want. And then multiply by the derivative of the inside. The derivative of cosine is negative of sine. So the negative cancel out. And then we plug in from 0 to 2 pi. And cosine of 0 and cosine of 2 pi are the same. So this comes out to 0 as well. Whatever they are, they come out the same. They come out so they equal and opposite. So this is 0. Okay. Okay. So the idea of that was we wanted to integrate some curl vector field over some surface. And we weren't really excited about computing the curl or integrating over the surface. So we tried replacing the surface with its boundary curve. And because things were nice on the boundary curve, a lot of things canceled out. And we were able to compute it using Stokes Theorem. Questions or ideas? Okay, so it's kind of a crazy idea that you can replace a vector surface integral with a vector curve integral, a vector line integral on the boundary. You might wonder why you can just like replace one with the other. But we talked about, for Green's theorem, why Green's theorem was true. And Green's theorem was true because if you break up an integral of a curl over a whole region of the plane, it kind of cancels, everything on the inside kind of cancels out, and it's pushed to just the integral along the boundary of how the vector field is curling around. And Stokes' theorem is true for the same reason, but a dimension up. Well, taking the same picture and just moving it into 3 dimensions. So I thought I'd show that if you take Stokes' theorem and your surface is just something in the plane, it's exactly just Green's theorem. So we'll show that if your surface S is in the xy plane, Stokes' theorem is just Green's theorem. Okay, so suppose that you have some surface, and I'm going to draw in perspective here. Here it is, your surface S, and it's living in the xy plane. So here's x, here's y, and then here's z. So S thinks of itself as an xy plane type of person, but we're going to tell it, oh yeah, by the way, there's z. Okay, so Stokes' theorem, let's see. So let's apply Stokes' theorem to this thing. So Stokes' theorem says that if you have the vector line integral over the curve around it, this boundary curve, C of f dot ds, it's the same as the double integral over S of the curl of f dot d big S. Okay, as long as everything is compatibly oriented. So in Green's theorem, we always made sure everything was going counterclockwise. So let's orient this curve counterclockwise. If it weren't counterclockwise, everything would also work out. There would just be some negative signs in the proof. So let's suppose the curve goes that way. And now we have to orient S with the appropriate orientation. So should the normal vector to S be going up or going down? Up. Yeah. Yeah. One trick, well, you can just imagine yourself walking here. And if your left arm is over the surface, this needs to be the back of your head. Okay, and you need to be standing up, not standing upside down. Okay, so the normal vector to S, here it is. And we can actually say exactly what it is. It's 0, 0, 1. That's the normal vector to S. It's just in that direction. Okay, so the curl of f dot ds, that's the same as the curl of f dot a normal vector, a unit normal vector, times ds, an area differential. And so this is the same as the double integral over S of whatever the curl of f is, dot our normal vector, which was 0, 0, 1 ds. Okay, so now let's figure out what the curl of f is. So if f is p, q, r, actually, if we are only caring about S in the plane, this R is going to be 0, but it doesn't really matter because it will cancel out. So the curl of F is I, j, k as vectors times a partial with respect to x, partial with respect to y, partial with respect to z. Okay, p, q, r. This is how we usually calculate it. Let's figure it out. So it's, okay, but here's the deal. When I take this dot product, I'm going to multiply the first two components of this by 0. So I do not care what they are. So I am not going to compute them. I'm going to put this like whatever, comma, whatever in there. Because I don't care what they are. So it's whatever, comma, whatever, comma. Okay, now I'm going to do the last one. So the last one is a partial derivative with respect to x of q minus a partial derivative with respect to y of p. So that's qx minus py. Okay, so it's something, comma, qx minus py. Now I have not enough space, qx minus py. So that's the double integral over S of qx minus py ds. But we're just in the xy plane, so ds is dA. And that's exactly Green's theorem. Green's theorem, yay! So they're true for the same reason. If you understand why it's true for Green's theorem, just take the same picture and pull it up into 3 dimensions. Yeah, questions or ideas? All right, all right, all right. So in all of our examples of Stokes theorem, we've taken a surface integral of a curl and turned it into a vector line integral around the boundary of the vector field F. So let's do the opposite direction. So here is our surface. No, not a surface this time, a curve. So suppose our curve is this triangle, which goes like this. Here's the point 2, 0, 0. Here's the point 0, 2, 0. And here's the point 0, 0, 2. So this is the z-axis, the x-axis, and the y-axis. And that's our curve C. So curve, well, it could start at any of these points, doesn't really matter. Maybe it starts here, goes chick, chick, chick. So there's our curve. And F is a vector field. So let F be the vector field x sine e to the x, comma, minus xz, comma, minus 2xy, comma, z squared plus y. Okay, there's our vector field. And this is our curve C, this one that I've written out here. So integrate, compute the line integral over C of f dot ds. This is what we want to do. Okay, so option 1 is just to do it. Just do it. So we'll just have to do it in 3 pieces. So we'll parameterize C, this piece, and this piece. Each of the pieces is a triangle. And then we'll integrate this vector field over it. You could do it, but it seems like it might be a bit tough. First of all, there's going to be 3 pieces. And secondly, this vector field looks bad. So, but there's 3 pieces, and f is bad. Well, it's not that bad. I mean, I don't like to say that things are bad. Sometimes people say, oh, it's bad weather. I say there's no such thing as bad weather. There's just rainy weather or something. So it's not a bad vector field. It's just a bit tough to work with. You have to make sure you're wearing a jacket if you would like to work with this vector field. OK, so this is the first option. Option 2 is maybe just try Stokes theorem. So let's try Stokes theorem. So Stokes theorem says that this integral that we want, the vector line integral over our curve C of f dot ds, is the same as the double integral over a surface of the curl of f dot d big S, as long as when C is the boundary of S and C and S are compatibly oriented. Okay, so that's the idea of Stokes theorem. We've never gone this way before. We've always had a surface which had a boundary. But now we just have a boundary with no surface. So which surface? We could use any surface. The world is our oyster. I didn't bring it in, but you can imagine that I brought in some cool wireframes and a bucket of soapy water. And that now I'm taking this wireframe and dipping it into the triangular wireframe and dipping it into the bucket. Do you see it? And now blowing into it. And you can see all the different surfaces that have this triangular wire as their boundary. So there are many different surfaces you could choose, but one of them is the easiest, just the flat plane containing this triangle. So let's choose that one. If it doesn't work out, we can try some other surface, but let's try the simplest thing first. So let's choose this surface S. So choose S to be the flat triangle with boundary C. So that takes care of this. C is the boundary of S. And now we have to make sure that C and S are compatibly oriented. OK, so either the orientation to S is a vector going up like this, or it's a vector going down like that. Which one should it be? Yeah, down. Yeah. So one way you could do it is you could imagine that you're standing here and walking around the thing, and if you were to be doing that, your right arm would be over the surface. So that's wrong. You'd have to be upside down. So, or another thing you can do is if your surface is flat, then you can actually use your fingers to do the right-hand rule. Don't do it if your surface isn't flat. But if your surface is flat, you can point your fingers in the direction of the orientation of the curve, and your thumb points in the normal vector direction. OK. So indeed, our normal vector should be going down. There's our normal vector. OK. So S oriented down. OK, we should also get some kind of description of S. It looks like S is flat, so S is a plane. So S is part of the plane. Now we have to find an equation for the plane that contains those 3 points. So you know some ways to do that. You could find 2 vectors in the surface to find a normal vector, and then use a point. But if your points are simple, one way to do it is to guess and check. So try to come up with an equation that satisfies all these points satisfy. So one thing to notice is that the coordinates all add up to 2. So x plus y plus z equals 2. So once you have a guess, you can plot all your points in. And if all your points satisfy the equation, you know it's the right plane. And I believe that is the case here. 0 plus 0 plus 2 is 2 in any order. OK, so, but now we've put ourselves in a situation where we have to do a surface integral. Fine? So we need to parameterize the surface. So let's parameterize S. OK, so you could use any parameters you want as long as there are 2 of them. We could use r and theta. That seems like a bad idea because this thing isn't circular. Let's just try x and y. So x, our surface, as a function of x and y, is just, well, some point in the xy plane, x comma y, comma whatever z value you get when you plug in x and y. But we can do that by solving this plane equation for z. So z equals 2 minus x minus y. So 2 minus x minus y. And we got that because S is on the plane x plus y plus z equals 2. OK, so this is our parameterization. And now we want to know which x's we need. So where x and y are, well, usually we say something like theta is between 0 and 2 pi and r is between 0 and 1. But here, x and y have to be in this little triangular region here. So I guess I'll just draw a picture for now, and we'll figure it out later. X and y are in this region, that triangle there, just from 0 to 2, and the triangle creating under the plane. OK, so there's a parameterization of S. And now let's find a tangent vector. So the tangent vectors, we'll do the tangent vectors. And then we'll use them to find the normal vector. So the partial derivative of this parameterization with respect to x, that gives a tangent vector in the x direction. OK, partial derivative of this thing with respect to x is 1. Of this thing with respect to x is 0. And of this thing with respect to x is negative 1. And then partial derivative with respect to y is 0, 1, negative 1. 0, 1, negative 1. So to get a normal vector, we'll take the cross product. So xx cross xy. So it is 0 minus negative 1 is 1. And then negative of negative 1 minus 0 is 1. And then 1 minus 0 is 1. OK, so this is the normal vector to our surface. Let's check that it's the correct one, because either we get the correct one or we get the opposite of the correct one. What do you think? Not the correct one. Yeah, we wanted the one that goes down. And this one, well, it's kind of hard to draw vectors in 3D, but this is 1, 1, 1, which means x is getting bigger, y is getting bigger, and z is getting bigger. It's like going away from the origin. So I think you can see that the vector that we got is this vector, which is not the one we wanted. It's the bad one. So this one is the wrong orientation. So we'll use x, y cross x, x, which you could recompute, or you could remember that it's just the opposite, negative 1, negative 1, negative 1. OK, so that's what we'll use, the one that we wanted. OK, so now, what are we supposed to do? Yeah, question?
For the cross product?
Yeah.
Why is the y component 1 instead of negative 1?
Why is the y component 1? So when you do the determinant, the signs alternate.
Okay. Oh, okay.
So it's, I didn't cover it up with my hand because it's kind of hard for you to see maybe, but you do the opposite of negative 1 minus 0.
Okay.
So when you do a determinant of a matrix, the signs are plus, minus, plus, minus, plus, minus. So for just a 3 by 3, it's plus, minus, plus. Yeah. OK, so let's compute this thing. So what are we trying to do? We wanted the line integral over c, which is the double integral over S of the curl of f dot ds, which we know is the double integral over the region of the xy plane that we care about, of the curl of f, and then we plug in our vector parameterization. So x of xy dot our normal vector, so xy cross xx dx dy, or dy dx. Either order is OK. So let's do this. So this is the double integral over the region that we care about. That's going to be this region here, R. Of the curl of f, we're going to have to compute the curl of f. Let's do it. So I'll put it over here. So the curl of f, I'll write out the three parts of f. So we have x sine e to the x minus xz, comma, negative 2xy, and then z squared plus y. So that's our vector parts, and those don't really need commas. Then this is I, j, k. Those are vectors. And then partial with respect to x, partial with respect to y. Uh-oh. Here's I, here's k, j. Partial with respect to y, partial with respect to z. OK, let's do this thing. So for the first component, we do partial with respect to y of this thing, z squared plus y, 1, minus partial with respect to z of negative 2xy. Which is 0. OK. Comma, the opposite of, because the sign on the middle one is negative, partial with respect to x of z squared plus y, 0, minus partial with respect to z of negative xz. This whole thing, sorry, this derivative with respect to z of this first bit is 0, and then derivative with respect to z of negative xz is negative x. Minus 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 is minus, I think. So minus x. I believe, maybe I have that wrong on the sheet. Is that right? OK, minus minus minus. Always a struggle. And then finally, partial with respect to x of negative 2xy is negative 2y. And partial with respect to y of this whole thing is 0. So I think that's the curl of f. Just 1, negative x, negative 2y. Boom. OK. So now that we have the curl of f, we have to plug in our parameterization of our surface. So in here, we have to plug in for x, y, and z. But luckily for us, x is just x and y is just y, and we don't have any z's in our curl. So this is negative 1, no, positive 1, negative x, negative 2y, dot xy cross xx, that was the one that we wanted, negative 1, negative 1, negative 1, dx, dy. OK, so that's the double integral of negative 1 plus x plus 2y. Dx dy, or dy dx, whatever you want. And now finally we have to set this up. So if y is on the outside, then we just want to know y is going from 0 to 2. And then if you pick a y, you fix a y, and you see where your x's go, well, this line is x plus y equals 2, or x equals 2 minus y. So x should go from 0 to 2 minus y. OK. And then this is something that you can do, and it comes out to some number, like maybe 2. Yeah. So the idea there was that we had an integral over a surface, over a curve, and we replaced it with a surface. Yeah. Which is not the way that we've been doing Stokes Theorem before, but it also works. Yeah, questions or ideas? All right. All right. So something that you might be thinking about is that we didn't have to use this flat triangle piece surface. We could have used any surface. So yeah, that's the idea of the surface independence property of integrals. So here we go. Let's draw some pictures. OK. So suppose you have some surface, like maybe it's this beautiful bubble that you've been blowing in the wind. There it is. It looks something like this. There's your surface, and it's oriented outward for whatever reason. Fine, you decided it was oriented outward. Then Stokes Theorem says that, maybe this makes S1. So Stokes Theorem says that the double integral over S1 of the curl of f dot ds is the same as the integral over this boundary curve, let's call it C, of f dot d little s. Okay, fine. But then what if you kept this same curve C and you just deflated this surface a little bit? So now the wind isn't blowing quite as strong out there. Yeah, oh, I forgot to orient this curve. Yeah, which way should it be oriented? Standing up, left arm, walking away. I think it should be oriented this way. Is that right? So if you're standing at the bottom, you see the person's face. And if you're standing at the top, you see the person's back of their head. Okay, so it's oriented this way. So now these things have compatible orientations. We are so happy. So the same thing would be the case if we had drawn this picture first. We had done the double integral over S2 of the curl of f dot ds. S. Big S. Okay. Right? The same, if just ignore this part, this is Stokes' theorem for this surface. Same thing. Okay, and then I could write out this little line integral again. And what if this were just the flat surface, S3, oriented in the same, with the boundary oriented in the same way? It would be the same as the double integral over S3 of the curl of f dot ds. We should make sure these things are oriented correctly. So you can imagine that these normal vectors sticking out are like a koosh ball at every direction. So as this thing contracts in, because the wind is blowing less and less, these are normal vectors sticking out. And then this contracts more and more and more. And as it contracts in, they're just normal vectors pointing to the left here. So these have the same orientation. And then you could blow on it from the left, and you would get the same thing. Now we can see both parts of this. Now we have a surface going this way. So here's the back, and then here's the front. And this is our S4. And now which way should S4 be oriented? It should be the inward normal vectors, because you can imagine these normal vectors like getting pulled in. So these go in. So this is equal to the double integral over S4 of the curl of f dot ds, and so on. So on. You could make this blow out the other way to any kind of surface you wanted. So this is like surface independence of curl vector fields. In the same way that we had path independence for gradient vector fields. Because if you keep the boundary the same, you can move the surface any way you wanted. Just like if you keep the boundary of your curve the same, the boundary of a curve is its endpoints, you can move the curve any way you wanted. Yeah. Okay, so I think it's cool in its own right, and it can also help us to do impossible things. Okay, so they say that you should make sure you do at least 2 impossible things before breakfast. Did any of you skip breakfast? Great, so that will work for you. Okay, so suppose we have this crazy surface that looks sort of like a hand. So it would be more appropriate if it was Halloween, but it's not. So here's our surface. There it is. Okay, there's our surface S. And as usual, it's oriented outward because that's easier to draw. So this is actually a surface. Okay, does it look like, there, you see it? It's like a latex glove sitting in space. Okay, and we have some vector field, which is kind of a mess. So the idea is we're going to want to compute the double integral over S of the curl of f dot ds. And you are now asking, what is the curl of f? Well, the curl of f, this thing you're asked to compute, is y to the y to the y, sine of z squared, comma, y minus 1, e to the x, x perhaps plus 2, comma, some more stuff. Okay. Comma, what's the last thing? Z, e to the x, x. Fine. Okay, so you would like to compute this vector field over this surface. So there are a couple of options we have. Option 1 is always to just do it. Fine, just compute that over this surface. But we cannot do that because we do not have an equation for S. Can't do it because what is S? We don't have a parametric description for it. Fine, no problem. Apply Stokes Theorem. So Stokes Theorem says this integral that you want, this double integral over S of curl of f dot ds, is the same as a single integral over the boundary of f dot d little s. Great. So all we have to do is figure out what f is. That sounds hard. So we can't really do this either, because what is f? So hopefully you imagine that this is like a completely intractable problem. Okay, one thing that I didn't say is that this glove lives somewhere fixed in space. So I'm going to put it very much like our paraboloid that we did at the beginning. So that the y-axis is coming out here. It's cutting off at y equals 1. The x-axis is coming out here somewhere. And the z-axis is going up there somewhere. So it cuts off there at y equals 1. So maybe we could use the surface independence property. Let's try that. So the double integral over S of this curl of f dot ds is equal to the integral over the boundary curve of f dot ds. We already tried that. That doesn't work. But we could use any other surface that has the same boundary. So let's try just the flat disk. Let's call that S1. There's S1. So it equals the double integral over S1 of curl of f dot d big S. Let's see if we could make that work. It's possible. It's possible. Okay, so let's try this. Which way should S be oriented? Should it be oriented pointing to the left or pointing to the right? Yeah, it should go to the left. One way you can imagine that is that this glove has vectors pointing out everywhere, and then when you contract it, those vectors will be pointing to the left. So it's pointing to the left, and in fact we can say what this vector is. It's a unit vector pointing to the left, and the left is the y direction. So this unit vector is exactly 0, -1, 1. So we want to compute this. This is the double integral over S1 of the curl of f, which is that vector field. So that's something, comma something, comma something, dot this normal vector. Okay, I should write that down. This is the curl of f dot n ds. So that's the double integral over S1 of whatever the curl vector is, that nasty thing, dot 0, -1, 0 ds. So I don't care what the first and third components are, because I'm going to multiply them with 0. So it's something and something. And now let's look at the middle component. Well, on this surface S1, y equals 1, so this whole term goes away. So all we are left with is 2. So this is nothing, whatever, 2, whatever. So this is the double integral over S1. Let's take this dot product, something times 0, plus -1 times 2, that's -2, plus something times 0, and ds. So this is -2 times the double integral over this surface of ds, which is -2 times the area of S1, and S1 is just a unit disk, So the area is pi, so it's negative 2 pi. So that's like a magic trick. We have a surface that we don't even have equations for. We have a vector field that's complicated, and we're still able to integrate it over it because of the surface independence property. Kind of amazing. Yeah. All right, thank you.